Thank you for tuning into my talk. My name is Jessica Bikaun, although you may also know me as Jessica Moran. Today I'm going to be talking about my PhD research with the CRC for honeybee products, which has laid the foundation for developing a beehive breathalyzer for American foulbrood. So just in case you're unfamiliar with the disease, American foulbrood, or AFB as we call it, is a bacterial brood disease of honeybees that is fatal to the colony. An infection begins when a young larva is fed around 10 spores of the causative bacterium Panabacillus larvae. As the larva grows, the bacteria germinate and multiply in the larva's gut. And eventually the bacteria break through the gut wall, which causes a blood infection and kills the brood. And it can be a larva or a prepupa at this stage. The bacteria continue to eat the brood from the inside out, turning it into a gooey, sticky mass that has a really foul smell. And this is where American foulbrood gets its name. Eventually, the larval remains dry down to a scale that contains billions of spores, which can remain viable for over 50 years. These spores can quickly spread through the hive, contaminating honey and pollen stores and infecting more brood. And eventually, this leads to a fatal undersupply of worker bees. These spores can then spread to other hives, primarily through bees robbing honey or beekeepers moving material around. And this obviously leads to more infected and smelly hives. American foulbrood is considered the worst bee disease that we have in Australia. It affects honeybees in all Australian states and territories. And due to the fatal and contagious nature of the disease, the Australian honeybee industry biosecurity code of practice requires beekeepers to destroy the colony as well as hive materials that cannot be properly sterilised. This makes the disease incredibly costly in terms of replacing hives and lost opportunities for honey production and pollination, costing beekeepers in Australia millions of dollars each year. Unfortunately, most beekeepers are likely to come across AFB at some point. In 2006, a New South Wales survey showed that over half of the beekeepers had a history of AFB in their apiary. And over recent decades, the number of outbreaks has actually been increasing. As hive densities increase, particularly for pollination events, outbreaks are likely to continue increasing in frequency too. However, making these pollination events safe is proving incredibly difficult, as only about 10% of hives are checked for American foulbrood at the farm gate. And this is due to the time and labour required to diagnose AFB. At the moment, diagnosing AFB requires a skilled individual to open the hive and identify symptoms of the disease. This makes diagnosis difficult when beekeepers are running large numbers of hives or if they're novice beekeepers. So in a nutshell, we wanted to see if we could use AFB's foul smell against it. We wanted to know if we could develop a beehive breathalyzer, a sensor device that can detect and diagnose AFB from its smell in the beehive air, allowing for fast diagnosis without needing to open the hive. And this is because all smells are just chemical compounds in the air. When we smell a beehive, we're actually smelling the compounds that are given off by things in the hive. For example, from the honey, we could be smelling eucalyptol from eucalyptus nectar. The hive material can also release things like pinene from wooden boxes. And the bees themselves give off a range of odours, such as this brood pheromone, beta-cis-ocimene. So if two hives smell different, they must have a different combination or abundance of compounds. We know that hives with AFB smell different from healthy hives, but we wanted to know what the exact chemical compounds are that are released by the bacteria causing that foul smell. So I want to pause here for a second. Detecting AFB based on smell is not a new idea. However, previous work and other approaches have taken a black box approach. That is, they have been blind and haven't involved identifying AFB-specific chemical compounds. So for example, I'm sure many of you have heard about the use of sniffer dogs to detect AFB. And dogs have been incredibly good at detecting AFB, but we have no idea what they're actually smelling. The use of dogs in Australia has also been limited because trained sniffer dogs are in short supply and we can't mass produce them. Similarly, it is possible to collect a range of sensor data and then use machine learning to predict hive health. It's what a lot of current hive monitoring technologies use. However, chemical composition of beehive air is incredibly variable and much harder to interpret than something simple like weight. So using machine learning to diagnose AFB based on patterns in gas composition is incredibly challenging. Hive air data is incredibly noisy, and for the algorithms to be at all accurate, they would require enormous data sets. And this type of black box approach has been tried in Australia, New Zealand, and Europe, but so far no one has been successful. So instead of taking a blind approach, my PhD has taken a white box approach that has identified the specific compounds that are present in AFB infections. We used Metabolomics Australia's gas chromatography mass spectrometer, or GCMS, to look at the compounds in the air around diseased and non-diseased larvae. This expensive analysis was only made possible by the funding from the CRC for honeybee products. So I just want to express my gratitude to my supervisor, Dr. Julia Grassel, and the CER's CEO, Dr. Liz Barber, for taking a chance on me and this project. Similarly, I couldn't have done this without the samples of AFB that were supplied by DPIRD's bee biosecurity team and anonymous beekeepers. So thank you very much for your in-kind support. But moving along, the data that we get from the GCMS looks like this. Each peak is a different compound, and the taller the peak, the more abundant the compound is. And we can look up the identity of this compound based on its mass spectra in a database. So this is a simplified mass spec readout of a non-diseased sample of brood. This collection of smell compounds is what we call a volatile profile. It's basically a signature or a smelly fingerprint of that sample. When we compare it to the mass spec reading of an AFB sample, we can see that there are a number of compounds that are only present in AFB. But keep in mind, larvae are little sponges for smell. A lot of these compounds are from the hive materials or what the larvae have been eating. So that's why we needed to look at lots of samples to make sure we weren't getting excited about random compounds. If we make a plot of the volatile profiles of the samples, so that is, each of these points represents a sample's 100 plus compounds and their abundance, we can very quickly see big differences between American foulbrood disease samples and non-diseased samples. This is a nice confirmation that we can tell differences between AFB and non-diseased brood just from their chemical compounds. But we wanted to check that the volatile profile of AFB is distinct from other common causes of brood death. So I went back to the mass spec and collected some data on the volatile profiles of sac brood, another brood disease in WA that can present similar to AFB, and non-diseased larvae that I had killed with either heat or cold and then let decompose for a day. In doing this, I wanted to mimic what happens when we get chilled brood or when a hive overheats. And just with the volatile profiles of these samples, our model was able to classify the condition of brood as AFB, sac brood, or non-diseased, with an accuracy over 97%. I then dove into the analysis and identified 41 compounds that are increased with AFB. These are what we call biomarkers and are the key to the AFB volatile profile. This is a heat map showing the abundance of these biomarker compounds in non-diseased, heat and cold killed, and sac brood diseased brood on the left, and AFB diseased brood on the right. Each row is a different biomarker compound. Where it is dark, the compound is very abundant in that sample, and where it is white, the compound is absent. So you can see that these compounds are either in really high abundance or exclusive to AFB. These are the compounds that if we could use a sensor to pick them up, then we would have a tool for detecting AFB. I should point out that we do know the identity of these compounds. We're just not making that information public yet. But all of the results I've shown you are from lab experiments using larvae and pupae that we had removed from the hive. We needed to make sure that our method worked in the hive. That is, that we could even detect these compounds in the hive, that they were honest and accurate indicators of AFB, and whether they occurred at the beginning of AFB infections or only became abundant in advanced cases. So with the help of Tiffany Bates, I did a field experiment with healthy and AFB colonies so I could analyse the compounds in beehive air. We set up 8 hives and infected 4 with AFB. We followed the development of the infections over 3 months, analysing the volatile profile and manually inspecting the frames each week. And then after the infected colonies were destroyed, I spent an additional 3 months analysing all of the data that we had collected. So what did we find in the field? Well, in beehive air, we detected well over 100 compounds. We then searched for our 41 biomarkers that we had identified in the lab. However, we only found 19 of these. So for half of our biomarkers, they were excellent in the lab, many of them exclusive to AFB. However, they weren't detected in beehive air. So we can't make any conclusions about how accurate they are in the hive, although it seems they don't occur in high enough concentrations for our sampling method to detect them amongst all of the other beehive noise. Of those that were detected, a few behaved poorly in the hive. We had 4 of these low-quality biomarkers that were increased in AFB larvae in the lab. However, these biomarkers were present in similar abundances at all AFB levels, from healthy hives with 0 cells of AFB to advanced infections with over 100 brood cells of AFB. These compounds seem to be produced by other things in the hive. Whether that's bee pheromones or hive stores like propolis and honey, we don't know. But these biomarkers cannot be used to diagnose AFB from beehive air. So taking out the poor biomarkers, we had 15 biomarkers that were considered good quality. These were increased in AFB diseased larvae and occurred in higher relative abundances in AFB infected hives. And finally, narrowing down again, 4 of these biomarker compounds were considered high quality. That is, they were exclusive to AFB, only detected in AFB diseased brood and AFB diseased hives. And biomarker compound D, for example, was detected when there were less than 10 brood cells of AFB in the hive. This means that from beehive air, we can detect AFB early in the disease progression, preventing serious outbreaks. However, the method and the data I've shown you relies on skilled technicians and expensive mass spectrometry. So the next step is to turn this research and these volatile biomarkers into a portable sensor that can diagnose AFB from beehive air, effectively a beehive breathalyzer. And this needs to be a practical device that is both sensitive and accurate, delivering fast results while staying cost-effective and user-friendly, and also being robust, meaning that it can handle getting a bit of honey on it or being bounced around in a truck. The trouble is we haven't found any existing sensor technology for our biomarker compounds that tick all of these boxes. So supported by the CRC for honeybee products, AgriFutures Australia and UWA, Dr. Julia Grassel has assembled a team of experts to develop the sensors we need. However, in developing technology, we faced what's called a fast, cheap, good pyramid, where realistically we can only have 2 of the 3. So to be efficient in delivering our sensors, we have taken 2 approaches. I have worked on a fast and cheap approach, while Dr. Praveen has worked on a fast and accurate approach. I should point out that the cost of this development is actually the salaries. So as a student, I cost very little, whereas Praveen's postdoc comes with a bigger price tag. Both of us have used relatively cheap materials. So my fast and cheap approach has been a grey box. It falls somewhere between the black box and the white box approach. This beehive breathalyzer prototype that I built included 10 off-the-shelf gas sensors, which we chose based on the biomarkers. However, these sensors detect groups of compounds and give a single response value. This is where it becomes a grey box because we can't be sure exactly what they are detecting. Using this prototype, I conducted lab experiments where samples were presented and the sensor responses were measured. So each line on this graph is actually a different sensor's response. I then compared the sensor responses between AFB and healthy larvae. And for most of these sensors, we did see a difference between healthy larvae and AFB. We saw a greater response in healthy samples. This suggests that among the mix of compounds being detected, there are a number of compounds that are more abundant in healthy larvae than AFB. So when there are less of these compounds, the signal is lower, and we could use that to diagnose AFB. However, you might recall that back when I described our biomarkers, I mentioned that we were only interested in compounds that increased in abundance. The reason for this is that although a diagnosis based on the decreased abundance works okay for individual larvae, it's not particularly useful in the hive. This type of sensor would work well when all of the larvae are healthy and producing lots of the compound, giving a healthy diagnosis, and when all of the larvae are diseased and not producing much of the compound, giving an AFB diagnosis. Although at this point, you wouldn't really need a sensor to tell you that your dead-out hive had AFB. But the sensor won't work when only some of the larvae are diseased. In this situation, the compounds produced by the healthy larvae would actually mask the signal of the AFB diseased larvae, giving a false negative for AFB. So you can see how this would be problematic in the hive. But although that's where my PhD ends, it's not the end of the story or the project. Moving forward, we are using Dr. Praveen's fast and accurate approach. Dr. Julia Grassel's talk covers this in more detail, but to quickly summarise, Praveen has had great success in developing paper-based sensors which change colour when they encounter our best biomarkers. Our plan is to create something like the strips that you would use to test pool chemicals. That is, disposable paper strips with a number of these sensors that is used in conjunction with a handheld device which would suck air from the hive and read the sensors to give a diagnosis. Pretty exciting stuff. So this brings me to the end of my talk. Summing up, my PhD has identified compounds released from AFB that are specific to the disease and detectable in hive air. This means that we can now use a white box targeted approach for sensing AFB. Our preliminary results suggest that a fast and cheap grey box approach using general sensors won't work in the hive. But we're on track with the fast and accurate white box approach that uses novel sensors for our best biomarkers. Eventually, instead of having to spend time opening hives, diagnosing AFB will be as simple as breathalyzing a beehive. Using our device, beekeepers and biosecurity officers will be able to accurately screen hives for disease, keeping bees healthy and beekeepers in business. Thanks very much for coming to my talk.